wonderful introduction to our panel, and I'd like to now give the floor to Kristen Davis, who's going to talk to us about some coral reefs. Thank you so much.
Thank you, Francois, for giving a nice introduction to, I think you're going to set it up well. Unfortunately, I'm not going to be a whole lot more upbeat than Francois was in his talk. Although I think what's nice about the order of these talks is that I'm really going to be focusing on some of the ecosystem implications for climate change in the ocean. And important to Pacific Islands are the implications for coral reefs that support, that are not only nice for diving on and for biodiversity, but also support the world's ocean, the world's fisheries. And so we should all be worried about the state of coral reefs beyond a vacation destination. So today I'm going to focus on how these ecosystems are dealing with change. And so climate change affects reefs in three primary ways that I'll talk about. One is that as the sea surface temperature is warming, reefs have evolved to exist in a band of the globe where they have a particular thermal environment. And when we change that, then they experience thermal stress. And you may have been aware over the past few years of a lot of what's called coral bleaching. And in fact, in 2015 and 16, the National Oceanic and Atmospheric Administration proclaimed that we saw the worst global bleaching event ever. So many reefs around the world bleached. And corals, typical hard corals, are animal, they're plant, and they are rock. They're kind of all of this. So the coral animal hosts basically a photosynthesizing algae that gives it some nutrients. And then the animal builds a calcium carbonate skeleton, which is the rock part. Now, when the coral gets too hot, that symbiont can produce toxins that are bad for the coral animal, and the coral kicks out the algae. Now, corals can capture some food from the reefs, the water columns surrounding them, but if they don't reacquire an algae, which is what gives them their color, then they starve. So this bleaching is when the coral kicks out its symbiont and the color along with it. And what you see is that white calcium carbonate skeleton underneath. Sometimes they can survive and reacquire these symbionts, and sometimes they can't. Often they starve and then die. So another way that climate change is affecting corals is through, as Francois was talking about, the uptake of CO2 by the ocean actually pushes the water in the ocean to be more acidic. And that is important for corals because they are performing a kind of chemistry within their bodies to lay down their calcium carbonate skeleton. And that chemistry is a little harder to perform with acidic water. It takes more energy for them to build their skeletons when the water around them is even slightly more acidic. And as soon as you tax them energetically in one way, they have a harder time surviving and competing on reefs, which are a very competitive environment. And then the last way that climate change is affecting reefs is as the sea levels rise, reefs have to rise with the sea level if they want to be able to capture light. Those symbionts need to photosynthesize, so they need sunlight. So as the sea level is rising, reefs have to rise with it. And often we can see examples of islands where reefs haven't kept up with sea level rise over geologic timescales and have sunk. And sea level rise has other interesting implications for some of the things that I'm going to talk about, because the depth of water on a reef determines how much it heats up, or what kind of circulation, what kind of currents it sees. So today I'm going to talk about a couple of places that I've worked on reefs in the ocean, really looking at how local circulation and topography influences how the reef responds to climate change and to warming in particular. This is a picture from the fore reef, so the kind of where it's sloping down into deep water on an atoll in the South China Sea called Dongsha. And I'll talk a little. This is there's a lot of beautiful coral cover here. It's got a lot of corals growing all over, soft corals, hard corals. What you might be able to see, there's something missing from this picture.
Fish.
Fish, yes. This is, even though this is actually a Taiwanese national park, this reef, like many, is completely overfished. And there are poachers that come and take the fish from this reef, and use destructive fishing practices, and the coral, the reef can definitely suffer without fish, because fish, many of them are herbivores. They eat the algae, which compete for space with the corals. And so if you take all the fish away, then you take the thing that was cropping the grass and keeping this balance between algae and corals. And it's a whole lot more complicated than I just made it, but that's kind of the simplified version. So, all right, so I'm going to talk about some physical processes. So I'm a physical oceanographer. I live in the Department of Civil Environmental Engineering, and I also have an appointment in Earth System Sciences. But I typically think about physics of fluid flow. But then, my research centers on how that affects marine ecosystems. So we're going to talk about what are the physics that are driving flow over these reefs, and how do they create the environment that reefs see. And then I think a really intriguing question is, how do these affect how reefs may or may not survive? And so we're finding that some reefs seem a little tougher than others. Given the same heating, some reefs survive when others don't. And as a scientist, we want to know why. And as someone who cares about how an ecosystem is going to do in the future, we want to understand, is there anything we can do to confer more resilience to, or make sure we don't build a golf course right on top of the ones that were the only ones that could survive, right? So, okay. I think I've been through a little bit of this. Here's some pictures of a Samoan reef in American Samoa in 2014. Here we've got a lot of healthy coral. They've got their color. They've got their symbionts. In February 2015, after a very warm event, now you can see that all the coral is still there, but it's white, so they've lost their symbionts and they've bleached. And here in August 2015, even though they've got some color back, they're dead. They have algae now growing on top of the coral, but not a live coral animal. So this is definitely an example of one of these massive bleaching events. In 2016, Outside Magazine, I don't know if you've probably heard in the news about the Great Barrier Reef and the massive bleaching that went on in the Great Barrier Reef. In kind of a provocative journalistic piece, Outside Magazine pronounced the Great Barrier Reef dead. It's not all dead, but I think it's still an unfortunate. About 90% of the reefs in the Great Barrier Reef were affected by warming in 2015 and 2016. And while they are not all dead, it is interesting to understand how they may recover and what will take their place. And what are the services that are provided by that ecosystem that are lost to us now? Okay, so we know some things about coral bleaching. We know that rising temperatures cause coral bleaching, but we don't understand why you might have sometimes a coral bleached sitting right next to another coral that didn't bleach. There's some species difference in the thermal tolerance of different corals, but there's also some other factors that play a role. And some of those factors are flow, how the water is flowing around them, kind of transporting the heat. And some of them have to do with the history of an organism and what kinds of things it's gotten used to. So this is the National Oceanic and Atmospheric Administration produces predictions of coral bleaching. So they can predict when it's likely that a reef system will experience thermal stress and bleach. In 2010, I was working in the Red Sea, on the Saudi coast of the Red Sea, and they predicted a bleaching event. And we just so happened to have a lot of temperature sensors and current meters in the water at that time, and so we were able to observe this event and understand. And one of the nice things, one of the bright spots is that, fortunately, when one of these mass bleaching events happens, not all the corals die. This is a survey after this bleaching event on several reefs on the Saudi coast here, and looking at the variation in bleaching. And so bleaching varied with the coral taxa, so what kind of coral it was, the depth that the coral was living at, and the distance from shore. And so we wanted to understand, since we had some sensors in the water, what was driving these variations in coral bleaching. And to make a long story short, what we found was that a coral that was living in very close to another. So this is how a lot of these reefs in this area are shaped. You have this offshore side. You get the reef has grown up to within a meter of the surface, and then you have it deepens again on the backside of the reef. Often you get waves breaking, surface waves breaking on the offshore side of the reef, and it sets up the sea level just a little bit on that side. So the energy from the wave is sort of put into setting up the sea level here, and it pushes the flow over this reef. And so you get this water that's constantly flowing over the reef. And basically what you see is a very different thermal environment. So reefs that live kind of on the front of this reef see a pretty stable temperature every day. Every day their temperature goes up and down about 1 degree Celsius. Whereas on the back of the reef, because as this water gets pushed over the reef, the sun is heating it during the day, and at night it's cooling it off, and you have this really kind of small volume of water. On the back of the reef, corals that are living at the same depth, they're the same species, are seeing a very different environment. Every day the temperature goes up and down 4.5 degrees Celsius, which might not sound that big when we kind of think about our day-to-day. But for reefs, this is a big temperature change. And it turns out that during this 2010 bleaching event, these two communities responded very differently to that bleaching. 100% of the corals on the forereef, on this front of this reef that experienced this more mild temperature environment, died. Whereas only 25% of the corals on this side of the reef died. And so what we wanted to understand, that sort of, since so many things were similar between these environments, these are 200 meters apart, these reefs, we thought, well, is it this thermal environment, is this history of exposure that is conferring some resilience to these reefs? So we started to think about, what really shapes the heat content on the reefs, and I'm going to zoom through this. Essentially, I'm just performing kind of a heat budget on the reef, understanding what we understand about fluid flow and the transport of heat across reefs, to understand, and I won't go through that. In any case, what drives the what creates this thermal environment on the heat, what shapes it, are the waves breaking, pushing flow across this reef, and the sun, the heat from the sun, and basically ocean atmosphere heat exchange was really creating. And so because that was fairly simple, we could actually backtrack and predict what the thermal environment, at least the high frequency daily temperature ranges on these reefs were. And then if we could test this idea that reefs that see this more variable thermal environment might be a little tougher. Okay, so I wanted to take this idea past just the Red Sea. I wanted to see if this high-frequency variability could potentially identify reefs that were a bit tougher on a global scale. And so my student, Ariane, assembled in situ, so where we have temperature sensors on a reef, records from all over the world that are different scientists have taken, and either colleagues that I twisted their arm or available records that are posted online. And he assembled temperature time series as well as observations of bleaching events and how these reefs responded to a particular anomaly. And so, look, it turns out that many reefs worldwide see high-frequency variability in temperatures. And this is actually not an aspect of temperature environment that NOAA and scientists who predict reef bleaching use. We use monthly averages in time because they're easy to see from satellite products and global products. And so Ariane used these time series and multivariate statistical models to understand which of the what kinds of metrics can we use to predict coral bleaching? And it turns out that this high frequency temperature variability is the most important thermal metric for predicting the bleaching severity on reefs worldwide, not just in the Red Sea, as we saw in that first case. So we're pretty excited about that. Because what that does is it gives us a metric to find tough reefs, to find, I have a colleague who I worked with on this project who calls them supercorals. So now we are interested in finding these reefs, these corals, that can withstand thermal anomalies, temperature anomalies. And so in that vein, we went to the South China Sea to look at a reef that was from that picture on the first slide. This is Dongsha Atoll, and it is in a very extreme environment. And the extreme, the agent of extremism in this are a thing called internal waves. And internal waves are similar to the waves that you think of when you go to the beach. So we call waves that are between kind of less dense air and more dense water, we call those surface gravity waves. Gravity is the restoring force for some perturbation. If you lift up the water surface and you let it go, then it bounces around because of gravity. Internal waves, there are density changes within the ocean. You have warmer water heated by the sun over cooler water, which is more dense. And there are waves which propagate along density interfaces within the ocean, just like the waves that we see at the beach. And in fact, those waves can run and it's got lots of nutrients. It also sometimes has lower pH, which is an interesting thing. And those nutrients can essentially drive productivity on the reef and change the environment that these corals see. So these corals are living in an extreme environment. They see a lot of variability in temperature. They see a lot of variability in water column properties of all kinds. So this is another student of mine, Emma, who is studying reefs on Dongsha Atoll. And we went out there in 2014 and did some of the first kind of time series measurements. There haven't been many measurements taken on this reef, but we focused on the east side of this reef because that's where these internal waves are first shoaling. And we put current meters, so sensors that measure how the current's flowing, the temperature and salinity of the water column. And then we use this other sensor, which is kind of new to oceanography, which is, I think, really exciting. It's a fiber optic cable that you can measure temperature along the cable. I won't spend a whole lot of time. This is my very simple cartoon of how it works. Essentially, you send a coherent laser pulse down the optical fiber. You get a spectrum of backscattered light. And if you understand the optical properties of your cable, you get, from this spectrum, you can back out temperature with distance along the cable. And so here is, we're putting this out on the reef. We had to build a scaffolding system on the top of, there's no dry land out here, so we built a scaffolding system in a sandy patch to be able to put this system out and powered it by solar panels. And here's a movie, just to give you an idea of what this cable looks like. So this is swimming up the Four Reef slope. Oh, there it is. So this is, you can see right here, we have beautiful spur and groove formations where there's sand channels between a meter high or 2 meter high reef. This is the cable, it's got meter markings along it, and so we're swimming up the reef slope. We had to kind of survey the cable to see where it's going. I'm going to zoom up a little bit. So this is a 4-kilometer long cable. Wow. So we're going up, up, up the Four Reef slope, getting shallower. Now we're on the reef flat, which is only about a meter deep. You see these beautiful seagrass communities and with some corals kind of spotted in there. And what we get from this cable is the ability to measure temperature over continuously, spatially, over 4 kilometers. So this right here, what I'm showing is kind of an example of data just from the reef crest right here, where the waves are breaking, and then offshore down the slope. So this is time. I'm going to orient you to this plot. This is time, about 6 hours. This is distance from the reef crest, so this is shallow, and this is going down to about 50 meters deep. What you see, the color is temperature. So warm colors are warm temperatures, cool colors are cool temperatures. You can see that shallower, it's warmer, which is what you would expect. Deeper, it's colder, which is also what you'd expect. This is an internal wave shoaling on the forereef. So this is all underwater, right? So this is a cold front, a change in temperature of 8 degrees in less than a minute, which for corals is a big shock of temperature. But there's, you saw, there's a lot of corals living in this area, so they have evolved, they've figured out how to deal with that kind of temperature stress. Okay, so there's lots of cool internal wave physics that we can do with this measurement. I won't go there. But what we can see, if this is 8 days stacked of a DTS cable, this is the part of the cable that's over the reef flat, and then this blue part is the one that's kind of going down the reef slope. And we can track these different masses of water as they get dragged across the reef with all their very different properties to help us understand how these reefs, which are some of the fastest growing corals that have been measured, we can measure their growth rate by taking a core and looking how fast they extend their calcium carbonate skeleton vertically each year, and what is conferring them this fast growth rate. And also, with different anomalies, we can understand how they might survive anomalies better than other high sea surface temperatures, better than other reefs. I think I'm probably pretty close on my time. How am I
You're
doing?
getting close.
Okay.
Couple minutes.
Okay, last thing I want to say is that when we, as scientists, get together and talk about climate change and the different levels that we are willing to accept, we have to make trade-offs for how we are using energy and what kinds of changes we're willing to accept. Right now, we are talking about this kind of 2-degree mark, where we're saying, what can we do to limit warming to around 2 degrees, thinking that that may help us to avoid some of the worst effects on global ecosystems. And so I think that there's a lot of opinions about that idea, that whether we'll be able to make 2 degrees or whether that's going to avoid ecosystem consequences at all. But I think what's instructive is to know that even if we were able to achieve capping warming at 2 degrees, often how global warming or how climate change presents itself at local scales can be entirely different. So for example, in the South China Sea in 2015, there was a warming event. And the temperature in the South China Sea rose, but it didn't quite get to what the local kind of, if you took the NOAA metric, the coral bleaching metric, it didn't trigger that to say that there would be a bunch of bleaching at Dongsha. However, when we looked, we had instruments out on the reef. This is not cooperating. We had instruments out on the reef during that time, and even though here's the temperature offshore, it rose about 2 degrees, the sea surface temperature, which is not exactly the same 2 degrees that we were talking about before, but just for argument's sake, it rose about 2 degrees offshore of the atoll, but onshore, but on the reef itself, the warming was amplified because of local circulation. And the reefs that were on the flat bleached quite a bit and recovered a bit, but I think the point here is that just because we decide to try to take these kind of global averages and we have these goals for limiting things, at the local scales things can be very different because of local circulation. And the reason this warmed so much was because in addition to this warming, the winds stopped blowing and the waves stopped breaking on the reef, which slowed the flow down on the reef. And then the water just sort of sat there and just got really hot. Okay. All right. So I think that I'm happy to take any questions, or if you guys have any questions about this or other reef stuff, I'm happy to. Sure. Yeah.
So these unusual waves, how often do they actually hit the atoll?
They're not at all unusual. In fact, they are all over the world's oceans. Internal waves, We don't know about them because they're hard to see. Because we can
Particular,
see the waves at the beach, that, you know, the surface waves, because they are generated by, often by wind, and they're at an interface that we can, you know, we see all the time. But these density interfaces within the ocean, we don't have an easy way to see them. But the reality to them, but they are generated in the summertime on every tidal cycle. Every time the tides drag water over this topography, they depress the density interface on one side, and because of that depression, as soon as they slow down, then you've got something unstable. They basically have an unstable density arrangement, and then this instability propagates away from that spot. So just like the wind, you know, ruffling up the surface of the water and that propagates away, or a pebble goes into a lake and that propagates away, in the same way, these internal waves, the effect of the tide.
So you're a reef person, but, and apparently there's no fish there anymore, but wouldn't the fish have also had to adapt to these enormous temperature variabilities?
Absolutely.
Yeah, so that's not something you know that much about it.
Right now. I think that that would be fun to understand. There are still some fish there, but not as many as there should be. Yes?
Could you address the contribution of other man-made deleterious chemicals like suntan lotion? I just read an article a few months ago saying that that was a major contribution towards the demise of the Great Barrier Reef. Could you address that?
So I've certainly seen the same work that says that there are chemicals in suntan lotion that affect reefs, and I think that that is often some of these studies are done in a lab where you know, a controlled environment where you can actually say something about the changing one factor and seeing what effect that it has. But I don't know if I think it would be hard to say that that would be the biggest factor in the Great Barrier Reef. I haven't read that same article, but I'm a little skeptical as to how they would come to that conclusion. There are a lot of factors affecting the reef, the Great Barrier Reef: temperature, fishing practices, nutrients coming from land, creating an imbalance in the nutrients on the reef, and from what they have been in the past, ocean acidification, potentially pollutants coming from sunscreen. All of these are affecting, which is why it's so hard. It would be nice to be able to point to one thing, because then that would be easy to fix. But I think that's probably not likely the case. Yes.
The August current of Madagascar has a phenomenon, and I don't think many people know about it, but it has to do with the thermocline and the difference between the roaring 40s ocean current around Antarctica and it upwelling into the Indian Ocean towards India, and the monsoons coming down with very warm water. And there's a place where out in the middle of the ocean, it's really deep, it forms its own land. Literally, the cold water comes in and the waves will break up to 150 feet.
So you get some kind of convergence where the waves break.
Yeah, the cold water coming in over the warm water rushing in creates a...
So you're talking about internal waves?
An internal wave.
Yeah. Yeah, there are a lot of internal waves in a lot of different parts of the ocean, even though they're difficult to see. Actually, this satellite image of internal waves in the South China Sea is mostly because internal waves drive these convergent, so coming together, and divergent, going apart currents, and they change the roughness of the surface water. So when you pull water apart, like if you see an upwelling of water, how it gets really smooth, you break down those capillary waves, you don't have the surface tension to kind of have those capillary waves. So the sun glint on the ocean changes between the rough water and the smooth water. And that's how we can view these bands of internal waves in the ocean. But they are inside the ocean, the density interface. Yeah?
Are you seeing an increase in these rogue waves that because of climate change, because of the changing in the temperatures of the overseas or anything you've seen?
Yeah, that's a good question. I don't know if there has been an increase in rogue waves or really just unusually large
Yeah.
surface waves. I haven't seen anything that says that we've seen more now than we did before. No.
You said for some of the coral listening species have variability in their resilience. I assume it's genetic. Are they doing something physiologically?
That's an interesting assumption, but I'm
Okay.
not sure. So there's some work going on right now to understand how much can corals adapt versus acclimate. So adapt is evolution, right? How much can they evolve? Can they evolve fast enough to deal with these temperatures? But adapting is a different way of dealing with these changes, and that's over the lifetime. Can they just get used to over a lifetime? Can we, can I get used to if I just spent a week in Panama and it was getting used me adapting to the humidity in Panama? So can they get used to it? And evidence shows that actually both of those things are at work for corals that are dealing better with higher sea surface temperatures. That they are both evolving and adapting, that those are both playing a role.
When you're making these studies, are you systematically measuring the wind in any way?
In this case, we had a meteorological station on that same platform. So mostly when I do a study of trying to understand circulation over, in the shallows, I make sure there is a wind measurement nearby. Because that's important.
Some scientists are claiming that the waves breaking on the coast of California are getting higher. Is that related to climate change?
I don't know that study, and I don't know. So I wish I did.
I actually would believe that it lends itself to these El Nino seasons, which is surface water temperatures, which would increase wave sizes. Yes.
One last question. Okay, one last one.
Okay. I was just wondering, the difference between what you'd call crystal clear water, ocean water, and water that is got pollution and stuff on it, or the difference between the crystal clear water being able to absorb solar energy and the polluted water blocking the solar energy or holding it in.
So I think that the optical properties of the water column would affect where the heat is absorbed within the water column. So you can imagine if you have a water column with a lot of turbidity, no matter what it's caused from, whether it's naturally occurring particles from phytoplankton or or pollutants, that heat gets absorbed in those much closer to the surface, as opposed to an optically clear water column where that would be distributed a little bit more with depth.
Go deeper.
So, sorry, was there a follow-on? Was there a second part of the question?
Oh, it was just wondering
How would that-
if there was proof that clear, pure water is going to be better for global warming.
Well, but there's a lot of turbid water that is clean, natural water.
Oh, I see.
Within the ocean. In fact, off the California coast, we have really productive soupy water sometimes in the spring, but that's mostly just phytoplankton growing and it absorbs light as well.
Well, thank you very much, Kristen. That was